So from the time of the ancient Greeks, the philosophical nature of infinity has been the subject of many discussions. In the 17th century, with the introduction of the infinity symbol 1 and the infinitesimal calculus, mathematicians began to work with infinite series and what some mathematicians, including L'H, Tidal and Bernoulli, too, regarded as infinitely small quantities, but infinity continued to be associated with endless processes. As mathematicians struggled with the foundation of calculus, it remained unclear whether infinity could be considered as a number or magnitude and, if so, how this could be done. 1. At the end of the 19th century, Georg Cantor enlarged the mathematical study of infinity by studying infinite sets and infinite numbers, showing that they can be of various sizes. 1, 3. For example, if a line is viewed as the set of all of its points, their infinite number, that is, the cardinality of a line, is larger than the number of integers. 4. In this usage, infinity is a mathematical concept, and infinite mathematical objects can be studied, manipulated, and used just like any other mathematical object. Pronounced, omega is the first transfinite ordinal, the smallest ordinal greater than all the positive integers. In the von Neumann definition of ordinals, it is equal to the set of non-negative integers. In the Wiener hierarchy, the fundamental sequence of is. Using this hierarchy, the following holds. Fast-growing hierarchy is on par with Ackermann function and Wittgenstein function. It is the first function in FGH that is not primitive recursive. Hardy hierarchy, the first function in Hardy hierarchy, which is not a translation. Slow-growing hierarchy, the first function in SGH, which is not constant. However, if we are not working in the Wiener hierarchy, may be arbitrarily fast-growing. For example, letting where is a busy beaver function makes uncomputable. In fact, there are as many fundamental sequences for and for any other countable ordinal as the number of monotonically increasing functions, that is, continuum, of them, is the first admissible ordinal. It is also the first transfinite regular ordinal, pronounced epsilon 0, epsilon null, or epsilon naught, is a countable ordinal, defined as the first fixed point of the function 1. The ordinal has several properties. Smallest ordinal, not expressible in Cantor normal form using strictly smaller exponents. Equivalently, this is the least non-zero ordinal that is closed under addition and, in fact, is also the least non-zero ordinal, closed under only. The proof-theoretic ordinal of Peano arithmetic and ACA0, arithmetical comprehension, a subsystem of second-order arithmetic. 2. Informal visualizations. Or, the second fixed point of using the Veblen function, using Buchholz's function, using Mador's function. Cantor's ordinal. pronounced zeta 0, zeta null, or zeta naught, is a countable ordinal, defined as the first fixed point of the function. 1. Note that some sources give the name to other ordinals. For example, Rathjen has used to denote the Fefferman-Schutt ordinal. 2. And Spius-Sapien has reserved the name for an ordinal for a sufficient although not currently complete extension of hyperoperators to ordinals. 3. It is equal to using the Veblen function, using Mator's function, and using Buchholz's function. Similarly to the epsilon ordinals, larger zeta ordinals can be defined as larger fixed points of the map. For example, is the next fixed point of this that is greater than, is the next greater than, etc. Formally, one fundamental sequence for is, and in general, and fixed points. Fixed points of the zeta function are sometimes called ordinals and also are equivalent to ordinals of the form where denotes the Veblen function. Written as eta 0 is a countable ordinal defined as the first fixed point of the function 1. It's equal to in Veblen's function, in Buchholz's function, and in Mator's function. The Veblen functions are a hierarchy of normal functions proposed by American mathematician Oswald Veblen in his article, Continuous Increasing Functions of Finite and Transfinite Ordinals, in 1908. 1. This allows obtaining ordinals beyond the limit of Cantor normal form. The modern version of the Veblen function is described below. For a sophisticated formulation using derivation, see derivative number example. The hierarchy is defined as follows: 1, 2, 4. The common / simultaneous fixed point of the functions for all. Thus, and so on, enumerates the ordinals, such that, and enumerates the ordinals, such that. For example, is a fixed point of both the functions, and, so far as well as, and is its third fixed point these functions have in common after and. Every non-zero ordinal can be uniquely written in normal form for the Veblen hierarchy, where 4, note, is the smallest ordinal, such that fundamental sequences for the Veblen hierarchy. Fundamental sequence for a limit ordinal is a strictly increasing sequence, which has the ordinal as its limit. Below denotes the nth element of the fundamental sequence assigned to the limit ordinal, where is a non-negative integer. Fundamental sequences for the Veblen hierarchy are defined as follows for limit ordinals. Written in normal form for the Veblen hierarchy 1.1, 1.2, and 1.3, 1.4, 1.5 for a limit ordinal, 1.6 for a limit ordinal, 1.7 for a limit ordinal. In rules 1.3 and 1.4 denotes function iteration, and infinite nesting with a Veblen hierarchy equals the Fefferman-Schutt ordinal. The Fefferman-Schutt ordinal, commonly denoted by 1, 2, pronounced gamma 0 or gamma naught, is the first ordinal unreachable through the two-argument Veblen hierarchy. Formally, it is the first fixed point of visualized as, or where, denotes the Veblen function. It's named after Solomon Fefferman and Kurt Sch. T. A common fundamental sequence of is defined as, and this is from this system. The Fefferman Sch. T ordinal is significant as the proof theoretic ordinal of ATR0, arithmetical transfinite recursion, a subsystem of second-order arithmetic. It is using the extended finitary Veblen function, using Buchholz's psi function, using Fefferman's theta function, and using Weyermann's theta function. The Ackermann ordinal is equal to using Veblen's function 1, using Weyermann's theta function, using Fefferman's theta function, and using Buchholz's psi function. See ordinal notation. It is the first fixed point of the map. and also smallest non-zero ordinal, closed under the three-argument Veblen function. The small Veblen ordinal is the limit of the following sequence of ordinals where is the Veblen hierarchy as extended to arbitrary finite numbers of arguments. Using Buchholz's function it can be expressed as, and using Weiermann's function it can be expressed as. Demonstrating the power of the Veblen hierarchy, this ordinal has been remarked as much greater than 1. For the growth rate of Harvey Friedman's tree, and function for unlabeled trees, a strict inequality 4, was proved. 2. The large Veblen ordinal is a large countable ordinal. In the Veblen hierarchy as extended to transfinitely many arguments, also called Schutzklammer-Symbolon, it is the least fixed point of the ordinal function. Using Weiermann's function, it can also be denoted, and is the first fixed point of. Additionally, using Mator's function or Buchholz's function, it is equal to. This ordinal has also been called the great Veblen number and denoted as 1. Jonathan Bowers has mentioned LVO order set theory while discussing hypothetical ways to beat Rayau's number without defining it. 2. In the fast-growing hierarchy, using Bird's array notation is approximately n 1 1 1 2 2 2. In the nested array notation, 3 and n 1 1 / 1 / 2 tilde 2 2 2. In the hierarchical nested array notation, 4. An ordinal collapsing function, OCF for short, is an ordinal function which is studied together with an associated ordinal notation in proof theory. One of the characteristic features of OCFs is that they output large ordinals using even larger ones, often uncountable ordinals. For example, Buchholz's OCF satisfies and where denotes the least epsilon number and denotes the Bachmann-Howard ordinal. In particular, an OCF gives a method of naming large countable ordinals using uncountable ordinals. For the use of an OCF in googology, see also the description of OCFs and why they're needed. There are many OCFs in use, often similar to each other and easily confused. Some even use the same symbols. As such, we should be careful when we read analyses which do not specify the OCF used. Indeed, many analyses cannot be trusted due to the lack of the actual definition of an OCF, that is, they might be referring to ill-defined OCFs. The most confusing fact on OCFs is that an OCF itself can never be an ordinal notation, although many googologists who do not know the precise definition of the notion of an ordinal notation state that OCFs are ordinal notations. An OCF is just a function defined in set theory, while an ordinal notation is a notation equipped with a primitive, recursive well-ordering and hence definable in arithmetic. Since the main use of an OCF in googology is the use in computable googology and an OCF itself is incomputable, the lack of an ordinal notation is a serious problem. In order to associate an ordinal notation, one of the easiest ways is to define a recursive set of formal strings, a syntax, on it as a first-order language so that the notions of a term and a function symbol makes sense, a structure of a language whose underlying set consists of ordinals such that the interpretation of some function symbol is given by actual ordinal functions such as an OCF, and construct a primitive, recursive relation encoding the relation for ordinals restricted to the underlying set of the structure. That is why an OCF is useful in the construction of an ordinal notation. However, to create an associated ordinal notation is much more difficult than to create an OCF. Therefore, stating something like, I created an ordinal notation, just by creating an OCF does not literally make sense. Actually, an OCF might not necessarily even yield an ordinal notation, because there is no justification of the existence of a primitive, recursive interpretation of the relation. Therefore, the situation is similar to the case where a googologist stated, I created a computable function just by creating a function using an Oracle Turing machine, which makes it doubtful that the work is a computable googlism. When we create a computable googlism, we actually need to provide an algorithm to compute it. For example, Googologists tend to simplify existing acts by dropping important conditions without understanding the reason why they are important. Since many complicated conditions in the original definitions are used in order to define the primitive, recursive interpretations of the relation, such poor droppings cause a lack of the primitive, recursive interpretations of the relations. It might fortunately admit an ordinal notation, but at least the creator needs to write down how to define the primitive, recursive interpretation of the relation. Otherwise, there is no evidence of the computability of the resulting work, and hence it should be just dealt with as an uncomputable Googleism. Extended weak Buchholz's function, Japanese. Is an extension of weak Buchholz's function, Japanese. Which is in turn a weak invariant of Buchholz's function. 1. 2. Weak Buchholz's function was defined by the Japanese Googology wiki user Heyoji, and extended weak Buchholz's function was subsequently defined by the Japanese Googology wiki user Atyu. The countable limit of extended weak Buchholz's function is expressed as where is extended weak Buchholz's function and denotes the least omega fixed point, and is expected to coincide with a countable limit of extended Buchholz's function, although the coincidence has not been proved yet. For more details, see the number analysis section.
3, 2.
Not to be confused with Buchholz's function or extended weak Buchholz's function or J. Buchholz function. Extended Buchholz's function is an extension of Buchholz's function by Googology wiki user Denis Maksimoff. 1. The countable limit of extended Buchholz's function is expressed as where denotes the least omega fixed point and is called extended Buchholz's ordinal or EVO in Japanese Googology. Contents. 1. Definition. 2. Ordinal notation. 3. Normal form. 4. Fundamental sequences. 5. Variants. 5.1 Extension. 5.2 Simplification. 6 Common misconceptions. 7 External links. 8 Sources. 9 See also. An ordinal is considered recursive if it is the order type of a computable well-ordering of a subset of the natural numbers. The Church-Kleene ordinal, then, is the first ordinal that is not recursive. An ordinal is recursive if and only if it is less than another recursive ordinal, so the Church-Kleene ordinal is also the supremum of all recursive ordinals, and the order type of the set of all recursive ordinals. It is a limit ordinal, since the successor of a recursive ordinal is also recursive. Since every computable well-ordering can be identified by a distinct Turing machine, of which there are countably many, is also countable. The omega fixed point is an ordinal, which is the fixed point of the normal function, or specifically the smallest such ordinal. When referred to as a cardinal, it is also called the Aleph fixed point. Is defined as the smallest ordinal with cardinality greater than. For limit ordinals, the limit of all smaller members in the hierarchy, the enumeration function of a class of omega fixed points is denoted by using Rathjen's function. 1. In particular, the least omega fixed point can be expressed as the omega fixed point is most relevant to Googology through ordinal collapsing functions. It is often expressed as using an unspecified or undefined function and the first inaccessible cardinal. For the issue on the function, see the main article on countable limit of extended Buchholz's function. See also. Okay guys, we reached the uncountable ordinals. Also commonly denoted. Called omega 1 or the first uncountable ordinal, is the smallest uncountable ordinal. It has several equivalent definitions. Call an ordinal countable if there exists an injective map from to the set of natural numbers. Is the smallest ordinal that is not countable. Is the second smallest infinite ordinal whose coffinality is equal to itself. Note that there are ordinals beyond that who have a coffinality of, for example, and is the supremum of all ordinals that can be mapped one-to-one onto the natural numbers, is the set of all countable ordinals. As every ordinal, it is the set of all ordinals less than it, is the smallest ordinal with a cardinality greater than. Note that with is also sometimes used to denote the power tower of the ordinal 1, 2, or to denote the church clean ordinal 3. The first uncountable ordinal is used in ordinal collapsing functions because 1, it is by default larger than any ordinal constructible in these notations. 2, we can conveniently use the word countable. In such contexts it is usually denoted with a capital omega, as in 4. An inaccessible cardinal is an uncountable regular limit cardinal. 1. The smallest inaccessible cardinal is sometimes called the inaccessible cardinal. The definition may differ depending on whether GCH holds. This number cannot be proven to exist within the FC set theory. Breaking down the definition, a strongly inaccessible cardinal must be a molocardinal or strongly molocardinal is an inaccessible cardinal such that the set of inaccessible cardinals below is a stationary subset of. That is, every closed unbounded setting contains an inaccessible cardinal in which the von Neumann definition of ordinals is used. The smallest molocardinal is sometimes called the molocardinal. The eponym molo has been appropriated as an adjective, so is a molocardinal may be referenced as is molo, for example. If we weaken both instances of inaccessible in this definition to merely regular, we get the weakly molocardinals. The two definitions are equivalent if the generalized continuum hypothesis is taken to be true. Furthermore, if is weakly molo and a strong limit cardinal, it is strongly molo. Neither molo nor weakly molocardinals can be proven to exist in the FC, assuming it is consistent, not even if we assume the existence of any number of inaccessible cardinals, also assuming it is consistent. Nevertheless, it's believed that the existence of these cardinals is consistent with the FC. A weakly compact cardinal, WCC for short, is a certain type of large cardinals with many equivalent definitions, such as this one. Let be all the two-element subsets of. Then an uncountable cardinal is weakly compact if and only if, for every function, there is a set, such that, and maps every member of, to either all 0 or all 1. More intuitively, any two-coloring of the edges of a complete graph contains a monochromatic subgraph isomorphic to. The WCC is always inaccessible and molo. Thus they cannot be proven to exist in the FC, assuming it is consistent, and the FC plus there exists a WCC is believed to be consistent. The least WCC, if it exists, is sometimes called the weakly compact cardinal. Let and denote the Levy hierarchy formulae. A cardinal is indescribable resp. If for every resp. proposition and set with there exists an with 1. Indescribable cardinals are the same as weakly compact cardinals. 2. Contents 1 Levy hierarchy. 2 size. 3 totally indescribable cardinals. 4 sources. 5 see also. The actual infinite was distinguished by 3 relations. First, as it is realized in the supreme perfection in the completely independent, extraworldly existence in God, where I call it the absolute infinite or simply the absolute. Second, to the extent that it is represented in the dependent, creatural world. Third, as it can be conceived by thought in the abstract as a mathematical magnitude, number, or order type. In the latter two relations, where it obviously reveals itself as limited, capable of further increase, and hence, related to the finite, I call it the transfinite and strictly oppose it with the absolute. Absolute infinity or absolute infinite is intended to serve as the supremum of all transfinite cardinals and ordinals. This idea has been proposed by Georg Cantor and is denoted as or 1. Cantor has linked this concept to the Abrahamic God. The collection of all cardinals is denoted Tab, also by Cantor, cannot have a cardinality, because it would lead to the Urali-40 paradox. 3. A portrait of Georg Cantor. A portrait of Georg Cantor. Absolute infinity cannot be also treated as a set of all ordinals for the same reason. Instead, it can be treated as the proper class of all ordinals, which is usually denoted by or. Unlike absolute infinity itself, the class frequently appears in Bugology. For example, it is used in the transfinite induction and in the definition of little Vigenin. 4. Note that absolute infinity is a well-ordered class by itself if we identify it with every initial segment of it is an ordinal. Spaius Sabian stated himself that it is not considered an official transfinite number, and there is no such thing as a largest number. He denotes this by red. 5. However, the initial idea of absolute infinity by Spaius Sabian was thinking about it as the largest infinite number, which is paradoxical, and thereby the term absolute infinity is not commonly used in the meaning of. In that case, it might be better to informally think about absolute infinity as some indefinitely large uncountable ordinal so that it is larger than any ordinal, for which we can pick a reasonably large system of axioms in order to define it. Spaius Sabian himself made a page showing that there are always larger absolute infinities in that sense. Absolute infinity or absolute infinite is intended to serve as the supremum of all transfinite cardinals and ordinals. This idea has been proposed by Georg Cantor and is denoted as or. 1. Cantor has linked this concept to the Abrahamic God. The collection of all cardinals is denoted tab, also by Cantor, cannot have a cardinality, because it would lead to the Urali-40 paradox. 3. A portrait of Georg Cantor. A portrait of Georg Cantor. Absolute infinity cannot be also treated as a set of all ordinals for the same reason. Instead, it can be treated as the proper class of all ordinals, which is usually denoted by or. Unlike absolute infinity itself, the class frequently appears in Bugology. For example, it is used in the transfinite induction and in the definition of little Vigenin. 4. Note that absolute infinity is a well-ordered class by itself if we identify it with every initial segment of it is an ordinal. Spaius Sabian stated himself that it is not considered an official transfinite number, and there is no such thing as a largest number. He denotes this by red. 5. However, the initial idea of absolute infinity by Spaius Sabian was thinking about it as the largest infinite number, which is paradoxical, and thereby the term absolute infinity is not commonly used in the meaning of. In that case, it might be better to informally think about absolute infinity as some indefinitely large uncountable ordinal so that it is larger than any ordinal, for which we can pick a reasonably large system of axioms in order to define it. Spaius Sabian himself made a page showing that there are always larger absolute infinities in that sense. Absolute infinity slash is intended to serve as the supremum of all transfinite cardinals and ordinals. This idea has been proposed by Georg Cantor and is denoted as or. Cantor has linked this concept to the Abrahamic God. This satisfies the full reflection principle. All cardinality properties are satisfied in this number, 1, which held by a smaller cardinal. It is the true limit of standard Bugology. Numbers don't make sense past this point, the very beginning of fictional Bugology and all other paths, ologies, and concepts. It is also a paradoxical number which claim no number can have a higher well-ordering in a set and bigger than this. There's way more numbers, fictional numbers, past absolute infinity. And there's way less than. As discovered since 2021, even though absolute infinity is a number, it cannot be defined as it is paradoxical in nature because no one number could represent all real numbers. Watch those 15 videos. How did he call the name?
Please. No. No, no, neither. No, no, neither. Alright, it's fine. Look at me. Look at me. Look at me. Look at me. Look at me.
That is already correct, and it was a meme.
Go back, just take it. They look good.
2, 3.
So leave a like and subscribe. So, warning, another jump scare in 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. Might not necessarily it might be better to normally think about there's no justification of the larger countable ordinal, so there is larger than any 1.4. We can therefore consider a system of similar to the case where the geologist stated that Sagan himself made a case showing just that there are always larger absolute infinity machines, which makes it doubtful that the work is a computable Googleism. When we create a computable Googleism, we actually need to provide an algorithm to compute it. For example, Googleologists tend to simplify existing acts by dropping important conditions without understanding the reason why they are important. Since many complicated conditions in the original definitions are used in order to define the primitive, recursive interpretations of the relation, such poor droppings cause a lack of the primitive, recursive interpretations of the relations. It might fortunately admit an ordinal notation, but at least the creator needs to write down how to define the primitive, recursive interpretation of the relation. Otherwise, there is no evidence of the computability of the resulting work, and hence it should be just dealt with as an uncomputable Googleism. I went so crazy summoning all the media and it was 1 gigabits.